and hand over to Ken to get us through the first item on the agenda.
Hi, everybody. I want to make sure, I'm going to share my presentation here. Can you see that, the red screen? And can you hear me?
Yep, it's all good.
Excellent, fantastic. Let me apologize first, because if you hear any snoring in the background, that's actually my dog. I've been through this presentation many times and obviously bore her to death at this point, and hopefully that won't be a common reaction. But there you have it. I am a developer on the Apache Cupid project. That's a project that deals with open source implementations of AMQP-based messaging components. I also am a member of the OpenStack Foundation, core committed to their messaging library, Oslo Messaging. I've been in the telecommunication field for more years than I'd like to admit. But my current interests now are like really large scale parallel and distributed communication systems. So today I'm going to talk about the AMQP protocol, which is where I've been doing a lot of my current development. This presentation is broken up into two sections. The first part of the presentation is we'll talk about what the protocol is and what it provides to developers that want to implement messaging systems. And the other part, the second part, will be more of like a stepping back and looking at how AMQP is deployed in a massively distributed cloud scenarios, and what components and infrastructure tools are out there to do that. So this conversation will kind of start with small bits and then build up. So if at any point I say something that's unclear, please stop me. I don't want to lose anybody, and ask questions. Feel free. I think there's actually a link to these slides somewhere we'll make available as we go forward. So with that said, let's start with a quick background. Excuse me. AMQP stands for Advanced Message Queuing Protocol, and the word queuing there is in italicized, because when it was originally designed, it was designed as a client-server protocol, and the server being the broker, and two communicating clients had to communicate through a broker, through a queue. That's no longer the case. That was back in the stupid ages when this thing first started, and it seemed like a good idea to have all your messages go through a single point. That doesn't scale up well, as you can imagine, right? So queuing is possible, but it's not built into the protocol. We'll talk about that some more. It was started back way back in 2003 by a consortium of banking companies led by JP Chase. Their purpose was to create an open standard for middleware messaging that could be shared in the banking industry, and that kind of started the ball rolling. Then not only were they working on this standard, this paper, but they were also trying to prove the pudding, if you will. They created an Apache Cupid project. That's a project I'm currently a committer on for actually implementing the protocol, client libraries, server libraries, brokers, things like that, to prove it out. So there are many iterations over the years of improvements, feedback into developing this protocol. Eventually, this group of interested parties went far beyond just the banking industry. It expanded to like something over like 20 contributor entities at the time. So it was disbanded as this kind of informal thing and created it was reestablished an OASIS working group. And companies such as Red Hat and Microsoft, VMware, and the others worked on producing the standard. It was eventually produced in 2014 as version 1.0. And there's links here to the actual standard. It's an open standard. It's not encumbered, right? You can click on that link and you can actually develop it for yourself, learn about the other protocols defined. And there's a working group, which is the second link that continues to add value and refine the various parts. So as a developer, as somebody who wants to develop applications, send messages, what does it bring to the table? Well, first of all, it's a middleware application level protocol. That is, it's not meant to be implemented as part of an operating system or from a particular vendor is OS independent. It's all at the application level. It's layer 7. The only thing that it really depends upon is a reliable network transport, and that's typically TCP. But aside from that, it's totally user space. And of course, it's an enterprise messaging system, so it has to have support for common patterns of message flow, like request response, like a RPC mechanism, remote procedure call mechanism, where request is sent, response is received. Also fan out or pub sub, where you have some entity periodically firing out events and many entities trying to consume those, right? That kind of fan out pattern is supported. And of course, queuing, right? Brokers store and forward messages. And since it's an enterprise protocol, it builds in defines very strict flow control. So you have efficient use of your resources and don't overrun consumers. We'll talk about that in a minute. And as I mentioned before, it's a peer-to-peer protocol. It's symmetric, right? There's no client-server action that's defined by the application. The protocol itself is just two peers. Going to the next, we were talking about this coming from the banking industry, so obviously security is important. Security domain starts at the connection level, at the TCP level, and it involves layers of security. The encryption layer typically is defined as TLS, SSL. That's layered on top of an authentication layer that can be used that's SASL based. So it allows different types of authentication mechanisms like Kerberos and things like that, or you play and log in if you're using encryption underneath or above. So security at the connection level. And the other thing is when you have multiple different disparate languages and clients all with their own, you have Go, you have Ruby, you have all these things trying to communicate. You want a way of accurately describing the data you're transferring. And that's a type system that's defined by the protocol that defines basic types like integers, different types of integers, strings, floats, and timestamps as binary types, right? Nothing is converted to ASCII and sent as ASCII. It's all, compact and binary. It also defines higher level container types like maps and lists, so you can build these, very deep and structured datagrams. The interesting thing here is that these lists and maps they're not type strict. In other words, you can have a list that has a string as its first element, an integer as its second, a map as its third. They're polymorphic. And it's also a self-describing encodec, which means that you can start parsing this binary body and determine, what its structure is. You can it'll start by saying this is a list, and the first entry is an integer, and the second, and it's so big, and the second entry is a string, and it's so large. So there's no need for pre-shared schema. Yeah, it's all self-described. Okay. So any questions so far? Cool. Okay. So other features of the protocol, obviously, when you have an application that sends a message, it usually wants to know whether the message got there or if it was rejected or failed. And that's also built in to AMQP protocol. As it's a peer-to-peer protocol, it essentially has acknowledgement that travels end-to-end. That is, the sender sends the receiver, the acknowledgement is proxied back. The other point that's key is that the addressing is layer 7. Its addressing is controlled and determined by the application itself. It's not network addresses, right? You use IP addresses, you use domains, hosts, and ports for setting up your TCP connections. But the messages that are addressed, when you send a message, you publish it to an address. Or when you want to subscribe to a certain type of message, you subscribe to an address. That address has nothing to do with the network address, right? It's simply an identifier used by the application to identify the source and consumers of a service, right? It's like a name of a service. Think of a name of a queue, for example. Is a good example of that. The protocol defines them simply as strings, so they're very flexible in how they can be used. The other thing is it's got to have efficient use of network resources, right? Nobody wants to create a socket per communication flow, right? Not if you can carve up your TCP connections, right? And multiplex multiple communication channels within them. And you also don't want to have blocking necessarily, right? You want to be able to send your messages in batches and deal with acknowledgements later at a later time and not necessarily block at the protocol level. So it's totally asynchronous.
Hey, Ken, can I ask a question?
Please do.
This is Cindy. So you mentioned like AMQP support async, like pops up messaging. So then how do we ensure the ACK acknowledgement? You know, for MQTT, there's a course like different levels to ensure the right deliverer between the server and client. What's the mechanism for AMQP?
So I'm going to get more into the actual deployment going forward. AMQP only defines a point-to-point mechanism, right,
Sure.
For acknowledgement flow.
Mm-hmm.
However, the intermediaries are allowed to provide their own, if you will, fan-in summary of acknowledgements, right? Mm-hmm. And there's a feature in the router that actually does that. It has different types of, for the different types of classes of acknowledgements that come back, it has a way of kind of summarizing them for you. If there's like hard errors, it will forward that along, indicating that something failed. Or if anybody accepts it, it forwards that along, so you know that the message was delivered. But it doesn't do any counting or things like that. It's not that deterministic.
So does it have a queue like on the server side?
The protocol is separate from that. There are intermediaries that will have queues like brokers and stuff.
See.
I'm going to get more into how that flow works and the
Okay.
components later. Okay, so
yeah, thanks.
we can talk more specifically to that.
Mm-hmm.
Oh, and the last thing I wanted to point out here is that it defines per message priority, which is useful if you've got a lot of traffic that is, say, low priority, like metrics and monitoring that's issued, and you have an alert, something high priority that needs to be processed. Priority per message priority is a signal to the message bus to prioritize the delivery of a high priority over low priority messages. Okay, and when we show examples of deployments, we'll talk about that a bit more. So I had a hard time naming this. What I wanted to kind of do is show you the various components that AMQP defines, the model and the objects. But I said I kind of focusing on the way the protocol operates at the wire level in this picture. The topmost of the object model is a connection, right? This corresponds to your TCP transport. The connection is then further subdivided into sessions, one or more sessions. And a session is kind of a resource and control sandbox. Multiple sessions are unrelated in that they can carve out their own bandwidth and reserve it. And we'll talk about that a little bit going forward. Then within a session, there's one or more links. This is where this is the concept of where messages are transferred. They're transferred over links. So as an application programmer, you're going to have a lot of exposure to dealing with link operations. The links are unidirectional. That is only in terms of the direction of travel of the message. Control information like acknowledgements travel back, but the message itself is unidirectional, which means that on one end of the link, you have a role that is a sender. It produces messages to the link. On the other end of the link, you have a role that's a receiver. It's consumed messages. The terms used in the protocol are source, a source of messages, and a target, a consumer of messages. And you might see that go through the document a bit. And I'm going to talk a little bit more detail on how this whole session and links things work going forward. And the last thing, obviously, is it defines a message, a protocol data unit, which I'll show you a little more detail on later. So having that in mind, how do you transfer a message? And as I explained before, you have a TCP connection over which one or more links are created. In this case, I'm showing you a single link in the topmost. You have two applications, two processes that need to communicate. The first step is to establish a TCP connection and do all your authentication, authorization, encryption at that level. And then a link is established through a negotiation process between a source and a target. And that link is then used to send messages from the source to the target, and acknowledgements travel back, right? The target can't send messages back to the source on that link. To do so, it would actually have to create its own source and its own target. So to do duplex communication, is the bottom, the second picture denotes that you have to actually have two links. In the case of, say, an RPC client, it's going to send a request from its source to the target server, and the server is going to, process that, and it's going to turn around a response. And in the message, it actually has the address of where to send the response to, which happens to be the RPC client on the left side. Links are actually very lightweight. They're really just an identifier in a message frame. So having multiple links to do that does not induce a lot of overhead. So that's how you do full duplex and single duplex transfer of messages. Now, so taking a step back, I'm taking that picture from the previous slides and kind of looking down, peering down the connection. All right, and this structure, you can see the connection in this particular example is carved up in two sessions. One session is denoted as the bulk session. That's where links that send bulk data are contained. There's also a control session that contains links for high priority occasional traffic, right? What you don't want to do is you don't want the bulk sessions to consume all your bandwidth, right? You want to be able to have some reserve for the control session. That's what sessions do, right? Sessions provide a way of preventing one set of clients from overwhelming another. And this all goes to flow control. AMQP, I said it had strict flow control. It defines two levels of flow control. The first level is what I just described, is at the session level. It's a byte window, okay? What this means is that it constrains the amount of memory on the receive side of each session to a certain window size. So you can't have more than an outstanding number of bytes across all messages, across all links. It starts at the default of like 4 gig, but once you set your window through configuration, you can negotiate that and obviously set it down. So that protects the memory of memory space of your application. The second level is per message flow. That is, that happens over the link, and that's a way of the receiver to back pressure a sender to keep it from overrunning. This is all very important. People don't tend to think about flow control, but without it, you will not be able to scale. All right, you generate these large backlogs if something should go wrong. That increases latency. That means things like RPC timeout and try to retransmit, and things get worse. All right, so you really have to have a well-designed, well-thought-out flow control protocol. And that's provided on two levels: bytes for memory footprint and link per link message flow control for controlling overrun and preventing senders from overrunning. And the link control is very simple. It's just credit based, right? Over the link, the consumer will give credit to the source. Credit is essentially the number of messages it's allowed to send at any time. So in this case, the target has communicated back through the link, you can send me 3 messages, and the application can send 3 messages. As the application sends 3 messages, it decrements its credit count, and once that goes to 0, it's blocked. This gives the application time to process those messages. Once it gets to a point where it's processed enough of those messages, frees up resources, it can then send back credits to the source. Now, this is what, as an application programmer, you're going to see a lot of this. You're going to deal a lot with credits. The session stuff is like set it and forget it kind of thing, provision and forget it, but credits are more dynamic. Okay, that prevents overrun. So the last part of the protocol I want to talk about is actually the message body themselves. The message payload is divided up into 3 sections that are mutable. The message bus can't change these sections. They're created by the sender and they're received exactly the same way by the receiver. The 3 sections are, there's a properties section, which is required, and that's delivery information. That has things like the to address, where this message is going. It has an identifier to help with identifying message duplicates and retransmissions. It's got a number of things in there, including a reply to field for use with RPC, remote procedure call, to tell the server where to send the reply. Then there's an applications property. That's metadata that can be used for your data. Things like encryption signatures or timestamps. It's optional, but it's there to allow you to have that separate metadata. And then there's data itself, which is any sort of the AMQP defined type that I explained before. Okay, so that's a quick run through of most of the features of the protocol. Now I'd like to kind of shift this to, you know, what does this mean? How does this work? What's the big picture? Building especially large distributed message bus. So if there are any questions on the protocol, I'd like to move forward to that. Okay. So how do you deploy AMQP, especially when you have something like this, where you have multiple sites distributed across geographic domain? And we talked about point-to-point links. We talked about TCP connections between consumers and producers. You can do that, but it doesn't scale well, and it's really a pain if you think about it, because you have different IP addresses, you have firewalls you have to punch through, maybe VPNs. It quickly gets complicated. This would be something that if you're doing over HTTP, for example, you probably have to do a lot of dancing to get this easily scalable. There's no need to do that with the AMQP protocol. It's actually no need to do it because the AMQP protocol we've built tools and facilities to build up infrastructures to avoid that kind of mess. All right. So I want to take a moment and talk about open source projects that build infrastructure components that help you build AMQP message networks. And of course, I want to start with the ActiveMQ Artemis broker, right? So there's this broker that communicates AMQP 1.0. So you have clients that can communicate with this broker. So you have broker services. It's a multi-protocol broker. It not only speaks AMQP 1.0, but it speaks other protocols like AMQTT. I'm sorry, MQTT. So that's a classic broker. People understand what that is. But the other thing is very interesting is the Qubit dispatch router. This is kind of a new thing in terms of messaging. People tend to think of message buses as being brokers. This is something else. The dispatch router, its purpose is to provide transportation through an AMQP network from producer to consumer. It's just like an IP router where you send IP messages, internet protocol messages through a TCP connection with an address and destination. You let the routers figure out how to get that to the eventual consumer. Right? This does the same thing, but at the application level, at the message address level. All right, and it runs a protocol. Instead of using IP addresses, it's using message addresses to determine the shortest path between producers and consumers. And it also has these delivery patterns that we talked about before, like multicast, and it implements multicast in the router. And I'm going to show you examples of how this is done. All right, and then the last thing is the Apache Qubit has a project called Proton, which does client libraries. Right, you don't have to implement AMQP protocol yourself. There are client libraries provide many different languages that are interoperable. So if you're creating applications, you can just pull this open source library for your particular language right off the shelf and integrate it. Right, so I'm going to start talking a little bit about these infrastructure components and how you build on them. Now, quick review of the different messaging patterns we've talked about. We've talked really about single producer consumer with direct connection, right? Send a message, receive the acknowledgement back. That's straightforward. When you have a broker really isn't a transport mechanism. It's a service. It's a storage service, right? In that capacity, it actually breaks the communication travel path between producer and consumer. It's actually a man in the middle. It acts both as a producer and a consumer. When a producer sends a message to the broker, that broker acknowledges receiving that connection. That's all the producer understands. That's all the notification the producer gets. It does not know if that message is ever consumed. It may not care. Like an event system may not care, right? And that's a good thing. It's good use of a broker. However, you want to try to do something that's synchronous over here, where the producer and consumer are expected to be online at the same time, like an RPC call. A broker is just overhead. it doesn't really lend anything to the efficiency of that kind of pattern. So now I'm going to introduce, having that in mind, I'm going to introduce the whole point of this dispatch router, this message router. The message router serves as the transport between producer and consumer, but it's transparent as far as the protocol is concerned. That is, the producer sends a message over its TCP link, which is actually terminated at the router. The router proxies that message through to the nearest consumer for that address. That consumer's acknowledgement is then proxied back. As far as the producer and consumer are concerned, they're directly attached, right? What it does do is it means they don't have to be directly attached via TCP. They can actually be completely disparate TCP connections. And that allows us to build this kind of messaging network where each site has these little edge routers. Right? That all the applications, all they need to know as far as TCP is concerned is how to connect to these edge sites, these edge routers. The edge routers are then connected to main core routers, right? You could have any configuration you want for these. These will be connected, obviously, with TCP connections. And then messages are basically sent from a producer onto the router, and then it takes it from there, and it will send it to the consumer via the optional path, optimal path. Okay, now you see I also have brokers here. They're not part of the transport, they're a service. So they kind of hang off these routers, providing store and forward where needed. So, I mean, what does this work? How does this work, right? What does it look like? I'm just kind of show you a smaller example. Here we have two edge sites, and we have a cloud site. Each one hosts the router. In this case, when these edge sites come online, these routers are going to have been configured with the TCP address of the B router in the cloud. Right, so these edge routers merely create their TCP connections into the service cloud, B. At that point, they start exchanging address information and determining where things live. Now, on the left-hand edge, we have a service A. That's a producer. It wants to produce to address B and C. In the middle, we have a service on the cloud. That is a consumer for B. That's where all B messages go. On the right-hand side, we have a consumer for service C. That's where all C messages will go. Well, service A doesn't really care, right? It connects to its local edge and it says, hey, send these messages. One goes to B, one goes to C. And it's totally transparent. It's up to the routers to handle handing off the B message to B and doing direct communications, if you will, through the cloud to C. All right? So this hides the complexity of the transport from the application, and it also provides inter-cloud connectivity, as in this example. So going forward, let's take a look at a flow message, right? The producer produces that message to the interior, its edge router, and then the router, by using a shortest path algorithm, finds the best path between producer and consumer. Okay? And that algorithm that's dynamic. If you reboot a router, it doesn't remember any of it. It just knows what TCP connections it needs to establish. And once they're established, it then begins communicating with its peers all the address routing information, and it learns it dynamically, no human intervention, right? So you can reboot one of these things and it comes back online. There's no quorum, there's no masters, there's no synchronization of that sort going on. They're fairly independent and pretty dumb. The amazing thing here is that since you don't have a single point of communications, you can actually have multiple parallel flows, right? These are actual parallel flows. They don't consume bandwidth, shared bandwidth, because they're traveling over different TCP IP connections. So what do you do with brokers? Well, like we said, a broker is a service. It's a queuing service, and you need to use it when you have the possibility that you need to store messages, right? Your consumer and your producer are not necessarily synchronized. The router is intelligent to understand what brokers do. It has some built-in smarts there. So when you configure the router to connect to a broker, it understands that the addresses on that broker, which are the queue addresses, the queue names, if you will, they're queues. And any producer that wants to send to that address will send to the queue. The queue is the owner of that address. It's the waypoint, right? It's the designated endpoint for producers. And consumers, just the opposite. Consumers from a queue address will be consuming from that queue rather than going direct to each other, right? And like I said, this is only used where you need to store, okay? So brokers are well integrated as a storage medium, store and forward medium. Now we have other patterns, like we have a single producer, multiple consumers throughout a very large network, producing a single message and echoing that, fanning that out. The replication is done by the routers, right? So at each point in the tree graph where you have, like, say here in the first, second, third hop, in here we have 3 branches where 3 copies of the message are made and sent out. And then further along to the right, we see 2 more copies are made. So the distribution load is spread where necessary. Now, to answer your question about what happens when you have all these acknowledgements coming back, that's a feature of the router. The router knows this is a multicast address, and it knows, for example, on the left-hand side, it's forwarded to 3 entities. It waits for the acknowledgements for all 3 entities before forwarding a final summary acknowledgement back. And the summary acknowledgement, there's no defined priority for them. Basically what the router does is it looks for any hard errors, any rejection because the message was bad. And it says, oh, look, somebody received this and rejected it. You got to know about that. So if the other ones accept it, the rejection is more important. Otherwise, if they come back as a few accepting it and maybe a few of them saying they can't deal with it now, the delivery has to be summarized somehow. So it's said as accepted. So it doesn't tell you, because there's no counting, it doesn't tell you how many consumed it, but it tells you whether or not something was delivered. And it also provides backflow, so the producer is gated by the rate of all those consumers. So it doesn't just keep hammering fan-outs messages. So that's interesting, but what's even more interesting is fan-in, right? If you think about edge computing, this is really what you want to deal with, right? You have a core data center that connects to a couple regional sites, and then a further connector to edge sites where the producers are located. Now you have a large number of edge applications generating tons of real-time data here, right? Say machine vision or something like that, right? You want to locally summarize that and process it because latency is important, for example. Right, so the messages are sent to the edge, and the edge can route locally, right? It doesn't have to send anything to a core. It realizes that there's an intermediary processing step right on the edge site itself, where all those messages go for processing and summarization before being forwarded to the regional site. So I'm just showing the example at the top here. I didn't want to draw the red lines. The processing can go to the regional site for maybe possibly further processing, or if you have, say, for example, an intermittent link or an unreliable link, it can be designed such that the messages are brokered and queued until you have a clear to send back to the core. Right? So now we're kind of seeing how brokers and routers work together, right, to provide that kind of reliable service. And lastly, high availability, right? It's always important. You've got a system here where links are going down, connections are going down, routers are rebooting. I already talked about the router. When it reboots, you don't have to intervene. It'll bring up the connections that it has from its internal configuration and then learn what's going on dynamically, right? You don't have to tell it, oh, these routes are here, these routes are there. It will learn from the network, from its peers. So keeping things simple and stupid are good. However, what happens if a connection fails? Just like an IP router, you route around it. So let's say this producer and consumer have this optimal path through the network for messages. Should that connection drop, the routers will detect it. They will reconfigure themselves and they will reroute around it. No human intervention. Right? Messages might get lost, right? You might not know them, but you will definitely get an acknowledgement back to the producer telling it that hey, I'm acknowledging these messages on behalf of trying to send them and not getting them there. And it will tell you whether the messages were actually forwarded and lost during forwarding, where they're in doubt, or the messages were queued up to be forwarded and the connection went down and it wasn't able to forward them and get like a no route to host, then you know that the messages themselves are not going to be duplicated in that case to retransmit. So there's a lot of intelligence built into these relatively simple routers. That's really all I have. The point of this slide is to kind of hammer home the idea is that this universal open protocol has a lot of universal open parts with it that are shared and easily leveraged. And there's a number of products out here that have support in one way or the other for AMQP messaging via plugins or integrations. This is real stuff. This is being used today. It's being deployed in the field. So that's enough of me talking. Are there any questions?
Yeah, I have one. Oh, by the way, let me introduce myself. So I'm Frédéric. I'm the new program manager for Edge and IoT at the Eclipse Foundation. Nice to meet you. It was certainly an interesting presentation. So I was wondering, it seems I was really not familiar with AMQP before this presentation. It seems as a protocol to be a bit more generic than MQTT in the sense that it supports a wider assortment of topologies or use cases. But apart from that, how would you characterize the difference between the two?
Well, I think what we look at when we look at AMQP is something that is essentially a full-featured enterprise messaging system. Having said that, a lot of these features don't have to be used. For example, acknowledgements. If you're producing messages that are idempotent, say you're producing temperature, as the current temperature, and each message that goes out supersedes the last one, you may want to send those as best effort and not require an acknowledgement back, right? So that makes things a little simpler. And there's a very number of things like this, like flow control. You can just, hard code a number of 10 and just keep updating it as you go. I don't know all that much about MQTT. I know it is very restricted profile and is a resource, specifically for resource constraints. If you are careful, I think you can achieve a lot of that with AMQP. I'm not aware of a embedded implementation for client library. That would be a nice thing. I know there's C library, but I think that relies on things like a POSIX kind of environment. But with flow control and limiting message sizes, I didn't really get into that. There's negotiation between sender and receiver, link negotiation, connection negotiation that says, I only support frame sizes of 512 bytes or whatever you want to configure, and that's honored. So you can use small bit data packets, and the encoding is very compact, so you can do that too. So I think there's ways of deploying this that will really minimize its footprint, and yet it has these larger enterprise features that could be used.
All right. And I think one more thing that distinguishes AMQP from other messaging protocols is this symmetricity that Andy talked about. So it's not a client broker protocol like MQTT or even earlier versions of AMQP protocol. So you can build different communication patterns like direct RPC between two endpoints, but you can also involve routing, you can involve brokering in a similar way as MQTT. So it adds a complexity, but it adds a lot of flexibility in how services can communicate.
All right, that makes sense. Thanks a lot for the answers.
I'm very curious about the routing part.
Uh-huh.
So Ken, you mentioned without VPN, the sites can communicate through the router. So I'm curious, can you share some details, like how can that happen, especially if the edge and all the sites are behind its own firewall settings?
Okay. Oh yeah. Well, that's a fairly fairly straightforward in that these are the these IP addresses that are used just to set up the TCP connections, they would have to be punched through a firewall.
Okay.
Right? But the point to remember, let me go back to a previous slide here. I know I'm still sharing. Let me go back here, right? Bingo. As long as the routers on the edge have a TCP connectivity to the service on the center, the IP domains, the subnets, if you will, they can overlap, right? You could have a 10 network over on the left edge and the same 10 network address over on the right edge.
Sure.
It's just that those ports that connect the routers have to be globally accessible, right? So the service and the IP addressing scheme on an edge doesn't have to leak over, right? You could have on the cloud in this particular case, we have public.
Yeah, that makes sense. I agree. Okay.
Okay.
But how can the router communicate to each other? Does that mean they can talk to each other?
Yes, they can. Actually, they're running a like a shortest path algorithm for routing. They do communicate with each other using their own dedicated links and channels that are dynamically established once the connections are up. With internal addresses, remember application addresses. So it's really running AMQP to communicate routing information.
Okay, I see. So can I say the assumption is all the routers are like either internet facing, they can communicate each other?
I'm sorry, you dropped out on that last one. I'm afraid my.
So I would assume like the assumption here is like between the router, all the routers, they can communicate.
Yeah, actually, there's a good point to be made there. In a routing network like this, these routers all know about each other,
Okay.
right? During the routing protocol, they know their neighbors and they know what other routers are out there. And the interesting thing is that if you have a management console, which the Qubit Dispatch router has a graphical web-based management console, if you have authentication and you can connect to any of these routers, you will actually be able to manage all of them because the management protocol of the routers is AMQP.
Okay. The code is, the open source code is the dispatch router project you just mentioned, right?
Oh yes, yeah, it's all at the Apache site. I have some links at the end of this presentation for follow-up stuff if you're interested. Yes, there are, there's an open source implementation, the routers Apache 2, and it's packaged for Debian, it's packaged for Red Hat RHEL stuff, and it's source tarball. Well, you can get it that way.
Yeah, very cool. Thank you.
Welcome.
One more question, like does this router expose some kind of the API endpoints, or these are the specific binaries deployable on the microservice architecture on the servers? Like suppose if I'm making an application and want to make some deployments, so can my client application communicate with this router in order to establish the connections, or?
Oh yeah, that's really the entire point of the router. The router is your on-ramp for your application, right? Your application merely needs to connect TCP connection to its designated router. And from that point, it can send messages to any service in the messaging network. Does that answer the question?
Yeah. So basically, like this router exposes certain API endpoints, or are they API based or totally binary based?
Well, the endpoints are the libraries for your application. Your application would use one of these libraries, perhaps from the Proton project. Say you're writing a Ruby or Go application. There's a Go library for making communication, for communicating over AMQP network. It has an API for creating a connection. It has a great API for creating a receiver for an address and a sender to an address. Then the ability to send messages and callbacks for receiving messages. So if you were to build an application, you would start there, right? You would pull that API in. and use that. And the API would, for example, when you're setting a connection, it would take an IP or domain name port, right? And it would set the connection on behalf, and then you have a connection object, depending on the language, of course. And that connection object, you can use it to create receivers and senders off of that, and then send and receive through the receiver objects and sender objects. So the only thing you really need is a library and an IP, right?
Yeah, cool. So once I go deep down on that, like understanding the different components, so definitely to do better clarity.
Yeah, if you go to that Cupid project, that link is on the screen. There's a couple places to look. The Cupid project has these various components in these libraries. There's also amqp.org, which is kind of the open consortium for all things AMQP. And that has pointers to other integrations and tools and like plugins for things like our syslog and various other systems out there.
Yeah.
So I'd encourage you.
Like after visiting site, like I see a lot of the links and they are pretty much descriptive. Thanks for bringing this.
Sure thing, yeah.
Hey, one more question. Great talk, by the way. Thank you for that. Really cleared some stuff up. I have a question regarding pod communication. So if I run two, for example, services on a pod, how does it, and it's on the same machine, basically. Does AMQP actually recognizes this and switches the protocol underneath, so it speeds things up? Or I know, for example, 0MQ is doing something like that, that they switch the protocol depending on the connections they can establish, for example, to use an IPC protocol.
Well, somewhat. I know the router has a HTTP service. So there's been work, although it's not really quite finalized yet, for HTTP mapping through the router into AMQP and back and forth, right? But typically, the router's connection, when you configure the router, you configure a listening port, right, for applications to connect in. And that port is, typically just speaks AMQP, but it can also be designated to speak either AMQP or HTTP. But you bring up a very interesting point. Something I totally glossed over is that the router has all sorts of different delivery patterns based on addresses. So in your case, you have maybe multiple services that are overlapping on a pod. The router can load balance between those based on the address if you tell it to. If you say, I have a certain address that's a work queue and I want to have several servers of that out there, you can load balance across it. It also has cost mechanisms where if one service gets backed up due to credit, right, exhaustion of credit, it will route the request to a parallel server, a different server that has less work on it. And I'm just kind of scratching the surface here, but there are different patterns to allow load balancing and locality, right? You can have a server that's a service that's local on your pod. You can have a service that's reached through the network on a totally different cloud that are the same services. You want to use the local service, unless it gets backed up to a point and fails where you have to then go out to the external service. The router does that for you. I don't know if that answered your question. Did that answer your question?
Yeah, the question comes a little bit from my view, because I'm trying to use or to analyze video data, and we are currently using about 15,000 frames per second from one camera device. And the question is, if I run it from one service, for example, like a camera reader or something like that, into another service, I don't want to use a network connection for that on the first hop, I wanted to stream it into my other application that's doing some pre calculations and then picks out the frames that maybe are interesting.
So this is kind of like maybe streaming through you're not streaming through a socket, are you?
Not yet.
Okay.
I'm not quite sure. I would love to just hook into the stream, but right now I'm just doing IPC calls. So yeah.
Moritz, this is actually something that I would love to talk to you about. I think probably outside the context of the meeting, just so we can go deep. But this is something that I've handled many times with sharing data between edge microservices without using network, and then using it when necessary to publish the results. This is so on point to what I see day to day. I'd be happy to help you out.
Oh, that sounds great.
Specifically regarding video, by the way. That's a primary use case for all this stuff. Yeah.
Cool.
All right. Thank you.
Excellent.
Dayan, do we want to make time for my thing? We've got only like 7 minutes left, or we want to leave more time for Ken?
Whatever you guys want. I mean, it took a little bit longer than we expected, but I mean, we can continue this conversation offline. So if you have more questions, I think, you know, Ken and I and everybody will be more than happy to answer it on the Slack or whatever. Just reach us. So, Kilton, sorry, will this remaining time be enough for you?
Oh yeah, that'll be fine. That'll be fine. I just want to introduce my thing and start some trouble. I actually want to start by saying, Ken, if I had an annual award for the best presentation in edge computing regarding technology, you would have just won it.
No!
I am such a fan of AMQP, but the thing is, it's funny, it's timely. We have, for Eclipse IOFOG, we just finished switching over to Artemis MQ because of all of these reasons, and it's not out yet, but as soon as it comes out, it basically is going to be saying the exact same things that you just said about how edge infrastructure should be running. If you don't mind, I might reach out to you to ask for a little bit of architectural guidance on best implementations.
I am, thank you for the kind praise. I am more than willing to help you.
Excellent.
And if I can't help you, I can hook you up with people who can help you.
Excellent. Yeah, we used to have this hodgepodge thing called IOMessage that was our version of handling a lot of this stuff years back. And we kept it in place until recently when people have been asking for, you know, the kind of self-optimization of pathways and stuff. And so anyway, I'm super excited to be doing the launch of that, but that's not out for another month or so yet. So thank you very much. And I'm glad this was recorded because this is seriously my favorite tech talk on this stuff in I don't know how long. So awesome.
Cool. Thank you. Thank you so much.
Yeah, great. So everybody, I'll share my screen and look at the security doc that I wrote this document last night so that I could finally kind of put my money where my mouth was in terms of writing this thing up and getting it into the working group. Can everybody see the edge security challenges Google Doc?
Yep.
Okay. So yeah, so I put this together, as I said last night, so it's not that long and it doesn't have that much in it yet, but the whole purpose, and I left the little ... after the, you know, I'm expecting fully to have a whole bunch of primary authors on this. This paper is intending to expose, as you'll see in the scope and the goals here, it's intending to expose the challenges that we face at the edge so that we can start to get a list that represents what industry is asking for. It's not going to solve it. And if this thing starts to get cluttered with a whole bunch of suggested solutions, I'm going to move them out into another document. So I'll be the watchdog of the goals here. What this thing has in it is, and I encourage you to read it and start dropping in comments. Please use comments for like major content changes so that we don't end up losing value. But if you're going to add anything, I think you can go ahead and insert it and then everyone will be reviewing and reading. But what this thing has in it is a bunch of sections on the different types of edge challenges for security. And so as an example, talk about trusting hardware and, you know, just, we all know that there's stuff out there that's already good, secure boot, hardware root of trust, et cetera. This is like a discussion around what challenges still remain. We all know that attached devices are a huge problem, right? It's like, how do I even know that the sensor is the right sensor and so on? These things come into discussion in this document. It's meant to be a living document until we decide that it's complete and want to release it to the public. And yeah, that's the gist of what this thing is and why it's here. And I want you all to, to look at it, give feedback and so on. Hopefully it provides some, some help for folks. there's like maybe 20, 30% more stuff that I didn't have time to drop in that's like in my notebook. So I'll be adding to it too. And feel free to also say like, this thing doesn't make sense. I want to change the structure. I'm open for commentary and all of that. So any questions, concerns?
Not at the moment from my side, but I'm definitely gonna go through.
This certainly looks very good, Kelton.
Cool. And of course, Frederick, it's great to see you on after we've been on 2 different meetings this morning. This morning, my time, I think it's a little bit later for you. Yeah, we'll, of course, from the Eclipse Edge working group, we will be focusing on implementation of solutions to these. And I think it's pretty safe to say that Eclipse Edge working group would be happy to share implementation and solution architecture stuff with this Kubernetes working group. So it's, you know, it's not a one-way street by any means, and you know, all stuff will circle around. But yeah, so that's where we're focusing on implementations more. And here I see this as, you know, this Kubernetes IoT Edge working group is a great place to talk about the demand from industry. And a great way to do that is to talk about what is everyone's security concerns, and that's a good starting paper before we start to solve.
So, Kilton, maybe we can put it on the agenda for the next meeting to go into the, you know, more details.
Oh, sure. And you know, by then we'll also have commentary from, you know, from the community. I'm happy to, Dan. And that one's going to be the flip time, right? So the what'll be an evening session for me. No problem. I'll put it on my calendar that you want me to be going into deeper detail then.
So let's organize around it. I'll start the threads about meeting times and all this, because there have been some questions around should we change times and again and do some things. So let's be in sync and, you know, organize it in the next 2 weeks.
Sounds good. And if it's helpful, if people can't make it to the different time zone oriented meetings, I'm happy to present in 2 different ones, or the recording, right, is a good way to distribute that, right?
Yeah.
Okay, great. Cool. All right, I'll stop share. And if anybody has trouble accessing it or whatever, I think the Slack channel has been where we've been kind of opening up stuff like that. Thank you, Dan, for opening access for me to drop this in.
No worries, no worries.
Cool.
Okay, great. I think that's all the time we had for today. Thanks everybody for joining in, and see you in the community.
Bye.
Thank you very much.
Bye.
Bye.
Bye. Thank you.